I just arrived.
Yeah. Anyway, you will see this is very easy. So Ghanesh is a PhD student. I will not risk it and name a number of years that he's been here, but he did first a project together with Tamer Zaki, and now is advised with Denise Game and myself, and he's working on wind energy. And specifically looking at the fate of vortices behind yawed wind turbines and the effects of a more realistic atmospheric boundary layer structure than what the previous studies had done. And he'll tell us about new results. Ghanesh, the floor is yours.
Thank you for the introduction, Charles, and good evening to all. So now I'll be presenting on modeling a yawed wind turbine wake in a conventionally neutral atmospheric boundary layer. I'd like to thank my advisors, Professor Game and Professor Menabu, and the funding agency NSF in supporting this research. And now I will start with the motivation behind the study. So yawing is an important technique by which one can control the overall efficiency of the wind farms, because yawing the turbine tends to deflect the wake away from the center line, by which we can either increase or decrease the wake interaction between the upstream and downstream turbines, using which we can control the efficiency of the wind farms. The goal of this present study is to model such a yawed wind turbine wake in more realistic flow conditions like an atmospheric boundary layer, where we expect wind veer to occur in an atmospheric boundary layer, but its effect is generally not included in most wake models. So we try to answer the question of how to include the wind veer effects in existing wake models. So what is wind veer, and what is exactly a conventionally neutral atmospheric boundary layer? So this is a typical sketch. This is a schematic sketch of an atmospheric boundary layer where there exists a geostrophic balance far away from the ground, which is characterized by a balance between the pressure gradient and the Coriolis forces, as we have a rotating Earth, and then we have, for large scale flows, we have effects of Coriolis forces. But as we move towards the ground, the presence of the frictional drag and the turbulent drag will contribute to the momentum balance that will induce the span-wise component of mean flow, which is called as wind veer. Now, for an atmospheric boundary layer to be conventionally neutral, we also, in addition to these rotation effects, we also need this temperature stratification, shown in this figure, where this red curve shows the temperature stratification, where above some height, there exists a capping inversion layer marked by the steep gradient in the temperature, and below this capping inversion, the flow is neutrally buoyant, and above the capping inversion, the flow is stably stratified. And so when such a boundary layer with both rotation effects and this temperature stratification is called as a conventionally neutral atmospheric boundary layer. And when we place a turbine under such an atmospheric boundary layer, it is going to encounter a mean inflow that has both streamwise and spanwise component to it, as opposed to a truly neutral boundary layer, where both the boundary layer and the outer region are neutrally buoyant, and it is driven by an applied pressure gradient, and we don't consider any Coriolis, like rotation effects, no Coriolis acceleration leading to no wind veer, such that a turbine placed under a truly neutral boundary layer will not have the span-wise component of flow, but just the stream-wise component of the mean inflow. Now, we previously saw that the yawing the turbine tends to deflect the wake, and the mechanism behind this yaw deflection is attributed to the formation of this counter-rotating vortex pair. The induced sidewash velocity from the CVP tends to deflect the wake away from the center line. So now we try to answer the question of how does wind veer affect the dynamics of the CVP, and how to model the effect of wind veer, how to model this CVP, including the wind veer effects. Now, before understanding the effect of veer, let's try to understand the existing model, both for CVP and the wake, in the absence of wind veer. So first, let's look at the CVP model in a truly neutral boundary layer, that is in the absence of wind veer. And at the turbine location, so how is the CVP generated? And in Shapiro et al. 2020, the CVP is generated because of this balance between, if we investigate this mean streamwise vorticity equation, we will see that there's a balance between the advection of the streamwise vorticity and the curl of the span-wise component of the thrust force. And for a known form of the thrust force, we can analytically solve this equation, vorticity equation, and then obtain an expression for the streamwise vorticity. And from this analytical expression, we can find the corresponding circulation strength and the cross-stream velocities using the Biot-Savart law, which, if we plot, will give rise to these contours which are obtained from these analytical solutions. and which pretty much explains why a CVP is formed in the first place, and it's basically because of the curl of the spinous component of the thrust force. Now at downstream locations, we previously saw that the CVP has this elongated structure, and if you look at different streamwise cut sections, the CVP tends to diffuse in the cross stream direction, and this is modeled in Shapiro et al. By solving an advection and turbulent diffusion equation, whose solution can be obtained by linear superposition of multiple point vortices. And from this CVP model of vorticity, which gives us the initial vorticity structure and the downstream evolution of the vorticity, we can find estimates for the decay of the maximum vorticity and the decay of the circulation strength. And then in Shapiro et al., it was shown that in the absence of wear, these estimates, analytical estimates, had a pretty good agreement with the larger dissimulation. So here the top plot shows the decay of the maximum vorticity, and the bottom plot shows the decay of the circulation strength of these counter-rotating vortices. Now, when it comes to modeling the wake in a yard, wake behind a yard wind turbine, in the absence of wear, there's a very recent study proposed. In Majid et al. Of 2022, they proposed a curled wake model. It's called a curled wake model because this wake model tends to capture this curled structure of the wake induced by these counter-rotating vortices. And this is the expression for the velocity deficit as given in Majid et al. And the different building blocks for this model it basically first models this maximum velocity deficit. These are the set of equations that models the decay of the maximum velocity deficit. And so the Gaussian term, the exponential term, some of the important terms are this wake width function, where the wake width expression for the wake width consists of these two terms, is kW times x, which is the wake expansion coefficient times x. So this physically corresponds to a linear expansion of the wake, plus an additional term that takes into account this curl structure of the wake. The curl structure comes from these the counter-rotating vortices, and the analytical expression model is proposed for a non-dimensional version of this wake shape. And the model consists of several terms which is basically a function of theta and a non-dimensional time scale. The non-dimensional time scale is basically non-dimensional using the circulation density, which is gamma of x by 2r. And this gamma of x basically takes into account the circulation strength of the counter-rotating vortices proposed in Shapiro et al. Of 2020. And then t hat is the expression this is the corresponding model for the t hat, the non-dimensional time scale. And then the last term that we have to model is the deflection, the yaw deflection due to the formation of the CVP, and also the presence of the ground will lead to image. Like we can model the ground by adding image vortices, so which will contribute to the deflection of the wake as well. And the corresponding term, the model for the yaw deflection is given by these expressions. So this is the curl wake model proposed in Majid et al. Of 2022, where without any wind wear effects. And then in this paper, they also show that this model has a pretty good agreement with the velocity deficit contours from LDS. So here, plot A shows for the contours for a 15-degree yaw angle, and plot B shows for a 25-degree yawed wind turbine, where the analytical model, we can clearly see that for larger yaw angle, it has this bean-shaped velocity deficit structure, which basically is trying to model the curled wake shape for the velocity deficit. So now, in order to understand, now let's see what happens to these, how to include the effects of wind wear in these curl wake model and the CVP model. So for that, we first do an LES of a yawed wind turbine, both in a CNBL, conventionally neutral boundary layer. So we'll have to remember CNBL will correspond to the boundary layer with wear, and the truly neutral boundary layer has no wear. So we have the LES is performed in two domains. One is the precursor domain and the wind turbine domain. The precursor domain we solve for the boundary layer equations, and which will result in incoming mean flow for the turbine in the wind turbine domain. And these are the corresponding plots. Plot A shows the resultant velocity. The solid line corresponds to a conventionally neutral boundary layer. Marker represents a truly neutral boundary layer, and the dashed line shows it's like basically these velocity profiles tend to follow a log law very close to the wall. Plot B is the streamwise velocity, where we can see that there is not much difference between both the truly neutral boundary layer and the conventionally neutral boundary layer. But the main difference comes in the span-wise component of the velocity, where you can clearly see that the CNBL has this veering velocity, whereas it is not there in a truly neutral boundary layer. So in a CNBL, it's going to have both components of velocity for the incoming mean flow, but for a truly neutral boundary layer, it is going to have only the streamwise component of the velocity. Now, from this LES, if we look at the contours of the time average streamwise vorticity, here plot A shows the time average streamwise vorticity from a truly neutral boundary layer where there is no wind veer, and plot B from a CNBL where there is, and then we can clearly see that in a TNBL, the vorticity has a structure that is very similar to the structure given by the analytical model from Shapiro et al. 2020. But in the presence of a wind veer, we can clearly the veer tends to disrupt the structure of these vortices. And also, if we investigate the circulation strength decay, so here the solid line corresponds to the circulation strength from the analytical model from Shapiro et al. The cross mark represents the circulation strength decay in a truly neutral boundary layer. You can clearly see that TNBL has a pretty good agreement with the theory, whereas in a conventional neutral boundary, the presence of veer leads to an asymmetric strength in the circulation strength of the vortices. The blue corresponds to the top vortex, and the red corresponds to the bottom vortex. Now how do we incorporate the effects of wind veer in the CVP model? So in the presence of background veer, the time average vorticity now has two components. One is the background veering vorticity and the CVP component of the vorticity, which means if I subtract the background veering vorticity, I'll be able to retrieve the CVP vorticity. And this is exactly shown in these contour plots at the turbine location, just behind the turbine. These are plotted at x equal to r, x by d equal to r, and then we can see plot A is the time average vorticity with veer. Plot D is from the once we subtract the veering veering component of the vorticity, we're able to retrieve this counter-rotating vortex pair structure that is very similar to the analytical model in G and the truly neutral boundary layer LES simulation. And similar is the situation for the span-wise velocity, time average span-wise velocity, where you can see that there is an asymmetric strength in the V, the strength of the V, but once we subtract the veering component of the vorticity, the V tends to look similar to the analytical model and the truly neutral boundary layer. The same thing happens at the downstream locations also for a CNBL. So the plot A shows the time average streamwise vorticity with the background veer, and once we subtract the veering component of the vorticity, we're able to retrieve the CVP structure of equal circulation strength that is very similar to a truly neutral boundary layer CVP. Yeah, so here we demonstrate that the circulation strength of the CVP after we subtract the veering vorticity has the same circulation strength as predicted by the analytical model. So the triangle markers represent the circulation strength of the vortices from the CNBL after we subtract the veer, which was previously, if we include the veer, it is going to give an asymmetric strength for the circulation strength. So which means that the presence of wind veer is not really affecting the CVP. It is just weakly superposes with the CVP vorticity. So this means that we can apply the Shapiro et al. Of 2020 model even in a truly neutral, even in a conventionally neutral boundary layer case, just by subtracting the background veering vorticity. Now, what happens to the velocity deficit model, the curl wake model? So here, this is the contour shows the downstream evolution of a velocity deficit, and the streamlines show the structure of the CVP after we subtract the veering velocity. And then, so this is the expression given by the curl wake model. And then we can see that in this line plot, which plots the decay of the maximum velocity deficit, the analytical model line, the curl wake model predicts this black line, which has a pretty good agreement with the velocity deficit decay from the LDS, from both conventionally neutral and the truly neutral case. So it has a pretty good agreement for x by d greater than 3. However, if I actually plot this contour from this model, we can see that the model predicts like a symmetric structure above Z. like it has this bean-shaped structure, but whereas in a CNB LES, it has this tilted structure. So the weir has some effect in advecting the structure of the wake. So here the plot B is plotted by considering only the yaw deflection due to the CVP. Now in the presence of weir, so we have this the veering velocity. We also have had some correction to this yaw displacement, which is proposed in Upker et al. Of 2018. So we can just add the displacement due to weir by this expression, v times a time scale x by u of z. Here the shear, so here v of z has this profile, it has a linear profile minus s times z, where we obtain the value of the shear rate from the LBS. And then if we add this additional correction to the yaw displacement, so the plot C is shown, plot C shows this analytical expression with this weir correction. And then we are able to get, retrieve a structure that is tilted and which is very similar to a conventionally neutral boundary layer. However, we also saw that such in a truly neutral boundary layer case, so this are the contours of the velocity deficit along with the CVP, along with the streamline showing the CVP structure. We also have this tilted structure even in a truly neutral boundary layer case where there is no weir, but we attribute this to the tilted structure of the vortices, which tend to advect the wake not horizontally but at some angle. So in conclusion, in a conventionally neutral atmospheric boundary layer, so the wind weir vorticity weakly superposes with the CVP vorticity. And if we subtract the background weir vorticity, we are able to retrieve the CVP structure, which has equal circulation strength. And we are able, so which means like we are able to apply the Shapiro et al. Model even in a conventional neutral boundary layer after subtracting the veering vorticity. And for applying the Majid et al.'s 2022 curl wake model in a conventionally neutral boundary layer, we just have to add this additional span-wise displacement due to the wind weir, which will retrieve the wake shape corresponding to a conventionally neutral boundary layer. As a future scope for the study, we are trying to understand the effect of, so currently we have looked at the conventionally neutral boundary layer case. So now we are going to consider the effect of the stable and unstable stratification within the boundary layer and how it affects the CVP dynamics. And also try to obtain analytical solutions to these mean inflow velocity profiles, and then such that we can use them in the wake models directly without extracting the information of the shear rate and others from the LDS. So that will be the future scope of this study. And thank you.
All right, thanks, Ghanesh. All right, so we have time for, you've left plenty of time for questions. So okay. Even here, I guess the students are to ask first, or postdocs. Any questions for Ghanesh?
Can I ask a question?
We'll go to faculty next, just see if there's any students. Otherwise, yeah, Denise, maybe go ahead.
Maybe I shouldn't be asking questions anyway, but so very nice presentation, by the way.
Thank you.
So, you know, I've been thinking about this. We've been thinking about this a lot. And so I'm wondering if this fact that the traditionally neutral boundary layer, you know, in this sideways velocity, does that mean that our theory is missing that? Like the original theory is really, you know, is it just that we're missing that aspect of the curling of the wake in that traditional theory? And that maybe if we had used, but I mean, we're using the theory from Majid, so some of that should be there. So I'm sort of wondering if you have a hypothesis of what that is, and you can say no, but I just, somehow it has struck me again. I think we've discussed this 500 times, but it struck me again when you presented it, that.
Yeah, so the Majid's model just, so this YC term is the yaw deflection term.
Right.
So this takes into account only the effect of the CVP and the effect of the ground. So it doesn't really take into account the effect of the weir. So that's what. So when we have a background flow.
But in the traditionally neutral one, there is no veer. So that's
Yeah,
what I'm saying
yeah.
is, and even here, when you showed the pictures of the machines model, you can still see some twisting of the velocity field. And you had said maybe it's because there's some extra sideways velocity here. And so I was just curious about that comment really that you made.
Yeah. So I was just talking about like so this Majid's model is applicable only for a truly neutral case.
Yeah, of course.
Yeah. So
remember the Majid model assumes that things are being advected at some velocity.
Right.
And the bottom, the velocity, the particles closer to the ground are moving more slowly. So they have had more time to evolve. So they actually, right, they move differently, but it might be going the wrong way. I don't know if this argument helps or not, but it's even for the truly neutral, the situation is a lot more complicated.
Yeah, no, it was just interesting to me that he had made a comment that we're not capturing some of the sideways velocity, and I kind of thought we were. That's why I was asking. But we can talk about it some other time. Maybe it's too complicated a question.
Yeah, so here this is like we have this additional term that
yes, but in the conventionally neutral one, you still have this behavior as well.
In the truly neutral.
Sorry, this one.
Yeah.
And you had said you thought that there was some additional sideways stuff induced here, and that's why we were seeing it here as well. And that's what I'm asking you about. Is the theory missing that? And have you thought about why?
Yeah, so as Charles was mentioning, like, so these two vertices, we expect it to move at the same rate, but they're not moving at the same rate.
No.
Yeah. We have Gretar, Professor Tryggvason.
Let's have someone else ask the question. I'm sorry.
I'm sorry to interrupt the meeting of the thesis committee, but when you look at aircrafts, trailing vortices beyond aircrafts, the fact that they scoop up a viscous boundary layer on the ground actually has enormous impact on how they move. Okay, they don't go infinitely out; they go up sort of and rotate around. Now, in your model, if I understand it correctly, you simply account for the ground by an image and no sort of vorticity generation at the ground. Is that correct?
Yeah, so we do account for the image effects for the yaw deflection.
Okay.
Yeah.
But not vorticity generation, as Gretar mentioned.
Yeah. We don't, for the model for the CVP, so we don't take into account the image vortices. Even without taking into account the image vortices, we're able to match the circulation decay and the maximum vorticity decay with the LDS. So,
okay, thank you.
Yeah.
All right. It's any other questions from anyone?
Just a sort of a brief sort of comment / question. So, have you thought about helicity? Yeah.
We haven't thought about helicity in this case. Like, why would helicity matter here?
Why would anybody do that?
I mean, I don't know. I thought it might be interesting. You have sort of span-wise vorticity and velocity along the same direction. So U dot omega might not be. I don't know. I'm just curious. Just a comment. Great talk, Ghanesh. By the way, yeah.
Yeah, thank you. Yeah, we haven't looked at helicity. So.
Well, I think I mean it's not necessarily a bad idea in the sense that sometimes in the core of the vortex you might have an axial velocity. If there was, right. I guess we don't see any evidence of x direction velocity peaks or minima at the core of these streamwise vortices. We don't really see that. You can see it in these pictures. There's no red or blue in these cores in the axial velocity, so it's probably very weak.
Okay.
Anyway,
might make a pretty picture.
Yeah. All right. Thanks. Let's thank the speaker again, and on to the next presentation.